Today we are going to discuss about a particular type of relation which is known as equivalence relation. So we start with the definition of equivalence relation, and then we move on to the some kind of results on equivalence relation and so on. And this is the definition. Equivalence relation. Let R be a relation defined on as known as set capital A, and R is said to be an equivalence relation if R is reflexive, and if R is symmetric, and if R is transitive. By the time reflexive, we mean that X is related to X for all X belongs to A. All elements in the set A is related to itself. Then second one, if R is symmetric, then that means X related to Y implies Y is related to X. Then R is transitive means X related to Y and Y related to Z, then X is related to Z. So that are the three important three axioms by which we define the term equivalence relation. So the same thing can be represented or written using three terminologies. R is reflexive, which means X is related to X itself for all X belongs to A, or the order pair X belongs to the set capital R, which is a subset of A cross A. So that's the definition of an equivalence relation. So when we need to check whether a particular given relation is equivalence relation or not, we check the following whether the relation R has the following three properties: reflexive, symmetric, and transitive. Now before moving into the properties of an equivalence relation, we define another term, which is partition. A given set A and an index set I, let AI subset of A for I belongs to I, then the index family of subsets of A suffix I, is a partition of A if capital A is the union of AI and AI intersection AJ is equal to phi, the null set, for all I and J belongs to I. So if we have a set capital A, then by the time partition, we are looking for an index in the collection of subsets of A in such a way that union of AI is equal to the total set A and the intersection is equal to phi. So this is A1, this is A2, this is A3, this is A4, this is A5 and A6, in such a way that the union will form the total set A and the intersection will form or intersection of any pair of AI and AJ is equal to the null set. So if such a collection of subsets can be calculated, find out, then the collection is known as a partition of A. So for example, if you consider the set of all positive integers, then that can be classified or partitioned into so if you consider the set of all positive integers, then it can be written as the union of two sets, the even numbers and the odd numbers. The union is equal to the positive integers, and we know that there is the intersection of even numbers and odd numbers is equal to the null set. So it's a partition of the set of positive integers. So that is the meaning of partition of a non-empty set. Now equivalence classes. So if you have an equivalence relation, then we can define the equivalence classes. And if X is an element of A, then the equivalence class of X is denoted by X in square bracket is defined as the set of all y belongs to A in such a way that y is related to x. So if we have say an equivalence relation defined on this set A, then and if x is an element belongs to A, then we collect all the elements of A which are related to x. Obviously it is reflexive, so x is related to x itself. Then there are many other elements of A which are related to x. So in some cases x is the only element which is related to x. In some cases there are a finite number of elements which are related to x, or infinitely many elements which are related to x. Anyhow, if we collect all the elements which are related to x as a set, then that set is known as the equivalence class of x. Now, the equivalence classes, which are if R is an equivalence relation, then if x and y belongs to A, then the following properties will satisfy. So, it's a theorem. If R is an equivalence relation, that means R has the three properties: reflexive, symmetric, and transitive. Then it has, or we have the following three properties. The first one, x belongs to the equivalence class of x. That's an obvious result because x is related to x itself, and therefore x belongs to equivalence class of x. So the proof can be written like this: x is related to x itself, this way. X related to x itself. That implies x belongs to the equivalence class of x. By the definition of equivalence class of x. Equivalence class of x is the collection of all elements in capital A which are related to x. So by definition of equivalence class and equivalence relation, x belongs to equivalence class of x. Now the second result says that x related to y if and only if equivalence class of x is equal to equivalence class of x. Equivalence class of x equal to equivalence class of y. So equivalence class of x and equivalence class of y are two sets, and to prove that two sets are equal, what we do is, if A and B are two sets, then in order to prove that A is equal to B, we take an arbitrary element from A and prove that x belongs to B, and we take an arbitrary element from B and prove that x belongs to A. And the first step, it means that A is a subset of B, and from the second step we can conclude that B is a subset of A, and this happens only when A is equal to B. So that is how we prove the equivalence of two sets. And here equivalence class of x and equivalence class of y are two sets. So we just start with an arbitrary element. Say A belongs to the equivalence class of x, and that means A is related to x, and just given that x is related to y. So A related to x and x related to y, and R is an equivalence relation. Therefore, using the transitive property, we know that A is related to y, and since A is related to y, A belongs to the equivalence class of y. And by this argument, what we start with is A is an element of equivalence class of x, and we conclude that A is an element of equivalence class of y. That means equivalence class of x is a subset of equivalence class of y. And if it's taken an arbitrary element from the equivalence class of y, then obviously that means that A is related to y. Then A is related to y and y is related to x. A is related to y, and what we have is x is related to y, and since it is an equivalence relation, by the symmetric property, y is also related to x, and by combining these two using the transitive property, what we have is A is related to x, and therefore A belongs to the equivalence class of x. So we can conclude that equivalence class of y is a subset of equivalence class of x, and from these two statements it is obvious that equivalence class of x is equal to equivalence class of y. So the second result, the equivalence class of x is equal to equivalence class of y if x is related to y. So if x is related to y, then equivalence class of x is equal to equivalence class of y. So if we take any element, so if we have an equivalence class x and the equivalence class of x contains a number of elements, say a1, a2, etc., then if we take any element from the equivalence class of x and consider its equivalence class, say equivalence class of a1 or equivalence class of a2, then obviously x is related to a1, so equivalence class of x and equivalence class of a1 are the same. Now the third result, either equivalence class of x is equal to equivalence class of y, or equivalence class of x intersection equivalence class of y is equal to the null set. So obviously if x is related to y, then equivalence class of x is equal to equivalence class of y. But what we have here is either equivalence class of x is equal to equivalence class of y, or equivalence class of x intersection y is equal to the null set. So in order to prove this, we start with assuming the converse of the statement, or if possible, we let equivalence class of x not equal to equivalence class of y, that means x is not related to y, and equivalence class of x intersection equivalence class of y is not equal to the null set. The combination or the negation of either equivalence class of x is equal to y or equivalence class of x intersection equivalence class of y is equal to the null set. So it is p or q. The negation is negation p and negation q. So as we have preliminary idea about logics, that's a simple example for proof by combination. Okay, what we are attempting to do is proof by combination. So anyway, here we assume that, if possible, we assume that equivalence class of x not equal to equivalence class of y, and equivalence class of x intersection equivalence class of y is not equal to the null set. That means there is an element in the intersection of these two equivalence classes. Let us consider that element be z. So z belongs to equivalence class of x intersection equivalence class of y. That means since z belongs to equivalence class of x, z is related to x, or x is related to z. So both are of same meaning because it is an equivalence relation. So let us write x is related to z, and since z belongs to equivalence class of y, we know that z is related to y, and by combining these two, we can conclude that x is related to y. But if x is related to y, this implies that equivalence class of x is equal to equivalence class of y. But we start with the assumption that equivalence class of x is not equal to equivalence class of y. So it's a contradiction, and that contradiction is due to our wrong assumption that equivalence class of x not equal to equivalence class of y, and equivalence class of x intersection y is equal to not equal to phi. So that proved our result that either equivalence class of x is equal to equivalence class of y, or equivalence class of x intersection equivalence class of y is equal to phi. So when we take a non-empty set A and define an equivalence relation R on the set, then that equivalence class generate a number of equivalence relation generate a number of equivalence classes, and that equivalence classes, say if X is an element, then there is an equivalence class formed by X. Then if you take another element Y from the set A, say here, then Y will form an equivalence class of Y. Then if you take another element Z, then if Z belongs to either of these equivalence classes, then the equivalence class are the same as that of X or Y. And if it is not, then there is a new equivalence class which is distinct from equivalence class of X or equivalence class of Y, and the intersection between two equivalence classes is either the null set or they are the same. If you take two arbitrary equivalence classes from the set, then they either coincide or they are entirely two different equivalence classes. So if equivalence classes has this particular property, then the set of all equivalence classes will form a partition of the set. So that's our major result. If A is a set, then any equivalence class or any equivalence relation on R induces a partition of A. So if we define an equivalence relation on a non-empty set, then that will induce a partition of A into equivalence classes. So if we consider the equivalence relation, say, okay, we will discuss about the partition of A in the case of different equivalence classes when we discuss some examples of equivalence relations or equivalence relations. Then any partition of A give rise to an equivalence relation R on A. So if we have a non-empty set A, and if we have a partition of the set A into a number of subsets in such a way that they are pairwise distinct and the union become equal to A, then that will induce a relation which is an equivalence relation. So the relation is very simple, belongs to the same set AI. So then another theorem, for any set A, there is a one-to-one correspondence between the set of all equivalence classes on A and the set of all partitions of A. If there is a partition, that will lead to an equivalence class, and conversely, if there is an equivalence class, then equivalence relation, then that will give rise to a partition of A. Then here we have a number of examples of equivalence relations, and the main equivalence relation, the most common equivalence relation is the equal to relation defined on any set. It can be the set of all real numbers, complex numbers, set of all matrices, set of all n tuples, set of all ordered pairs, xy, the ordered pairs on xy plane, or if we consider set of all polynomials, anything. The relation equal to relation defined on such sets will form an equivalence relation. So the proof is very simple. First one, A is related to A. If A is a real number or a complex number, okay, let's consider the case of complex number. Real numbers are too simple, so let's consider the case of complex numbers, set of complex numbers. Then if x plus iy is a complex number, then x plus iy is equal to x plus iy. Then the second case, if x plus iy is equal to a plus ib, then a plus ib is equal to x plus iy. Then third one, if you have three complex numbers, x plus iy is equal to a plus ib, and this a plus ib is equal to some c plus I into d, then we can conclude that x plus iy is equal to c plus id. So the first one is reflexive property, the second one is symmetric, and the third one is the transitive property. So we have all the three properties, and therefore that will form an equivalence relation. Then the second one is set of all straight lines on a plane, and we consider the relation parallel to. And if you consider two lines, then we can those two lines are either parallel to each other or not parallel to each other. So let's form an equivalence relation. So a straight line L1 is parallel to L1 itself. So the first property is satisfied. It is reflexive. Then second one, it is symmetric. L1 is parallel to L2. That means L2 is parallel to L1. And the third property is transitive property. L1 parallel to L2, L2 parallel to L3. That means L1 parallel to L3. So transitive property is there. So we have all the three properties satisfied here, and it forms an equivalence relation. And now in this particular case, what about the equivalence classes formed by this parallel to relation? The equivalence class of, say, a particular straight line. So let's consider the L1 be the x-axis. So x-axis. Then the equivalence class of L1 is the set of four straight lines which are parallel to L1. So there is a collection of all straight lines which are parallel to the x-axis. So there are infinitely many straight lines which are parallel to L1. Then let's consider the y-axis. So equivalence class of y-axis, L2 be the y-axis. The set of all straight lines which are parallel to L2, they are the equivalence class of L2. Then we can consider another straight line, say L3. L3 is something is in an angle to x and y axes. And the equivalence class of L3 form all straight lines, contains all the straight lines that are parallel to L3. Now observe that all these equivalence classes are mutually exclusive, or there is no element which belongs to two of these equivalence classes. It's not possible. So the equivalence class of L1 intersection equivalence class of L2 is equal to the null set. So it's a partition of our set of all straight lines. The set of all straight lines is partitioned into a number of equivalence classes. Now, in a similar way, we can define another equivalence relation in the xy plane. Let's consider the set of all circles in the xy plane, and two circles are said to be related to one another. So C1 and C2 is said to be related if they have the same center. So C1 is related to C1 itself. If C1 is related to C2, then C2 is related to C1. C1 related to C2, then C2 related to C3. That means C1 and C2 have the same center, and C2 and C3 have the same center. So C3 is a circle which have the same center as this. So it is something like this. And obviously C1 is related to C3. So it is reflexive, symmetric, and transitive, and therefore it's an equivalence relation. And the equivalence class of C1 is the set of all circles which have the same center as that of C1, or it's a family of concentric circles which is centered at the center of C1. And if we have another point, then we can have another family of concentric circles. And in that way, the set of four occurs in xy plane is partitioned into an infinite number of equivalence classes. Now, so that's the equivalence relation defined here. Now, the most important equivalence relation which we have to discuss is the congruence relation, and it is defined like this: A is related to B mod M if A minus B is divisible by M, or A minus B is a multiple of M, or A is congruent to B mod M if A minus B is a multiple of M, that is some K into M. So that's the relation, and we can check whether it is an equivalence relation or not. First one, A is related to A itself. Since A minus A is a multiple of M, so 0 into M, A minus A is a multiple of M. Then second one, if A related to B, that means A related to B means A minus B is a multiple of M, and that means B minus A is minus K into M, which is also a multiple of M, therefore B is related to A. Then the third property, the transitive property, A is related to B means A minus B is a multiple of M, so some M into K. And B is related to some C, that means B minus C is some L into M. So from these two expressions, if we add them, A minus B plus B minus C, that means that become A minus C is equal to K plus L into M. Since K and L are integers, K plus L is another integer, so it's an integer multiple of M. That means A minus C is a multiple of M, or it means that A is related to C. So it is the transitive property. So it has the three properties. It is symmetric, reflexive and transitive. So it is an equivalence relation. So A is congruent to B mod 5, or A is congruent to B mod 3. They are all equivalence relations. So this is an important type of equivalence relation which we will discuss in detail. So the important thing which we have to discuss about the congruence relation is about the equivalence classes generated by A is congruent to B mod M. So what's the nature of the equivalence classes generated by such a relation? So let us consider a particular case. Let's consider A is congruent to B mod some 3. A is congruent to mod 3. It is defined on the set of all integers, which is denoted by Z, which is the set of all integers, which is nothing but 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And on that set, I define the congruence relation A is congruent to B mod 3. Now consider the element 0. Then the equivalence class of 0 is the set of all elements which are related to 0. Or in other words, we are looking for the set of all elements in set of 0 minus or A minus 0 equal to a multiple of 3. Or in other words, A is a multiple of 3. If A minus 0 is a multiple of 3, then A is also a multiple of 3. So it contains the elements like, okay, or obviously 0 belongs to that set, then the elements like plus or minus 3, plus or minus 6, plus or minus 9, etc. These are the elements in equivalence class of 0. Now, what about the equivalence class of 1? Equivalence class of 1 obviously contains the element 1. Then what are the remaining elements? So we are looking for a set of all elements which are related to 1, or in other ways, x minus 1 is a multiple of 3. X minus 1 is a multiple of 3, or x is equal to 3m plus 1. A multiple of m plus 1. So it is 1, then plus 3 plus 1, that is 4, 6 plus 1 7, 9 plus 1 10, and so on. And in a similar way, it is minus 3 plus 1, that is minus 2, minus 6 plus 1, that is minus 5, and so on. So these are the elements in equivalence class of 1. And in a similar way, we can write down the equivalence class of 2. Equivalence class of 2, the only difference is here this 1 is replaced by 2. So all this 1 is replaced by 2. X is related to 2, which means x minus 2 is a multiple of 3, and therefore x is something like 3m plus 2. So, and that contains the elements like 2, 5, then 7 plus 1 is 8, 11, and in this side it is minus 2, minus 4, etc. So that is the equivalence class of 2. Then when we look at the equivalence class of 3, obviously this 3 belongs to the equivalence class of 0, and if x belongs to the equivalence class of y, then equivalence class of x equal to equivalence class of y. This is a result which we already proved, and therefore if 3 is an element in the equivalence class of 0, then the equivalence class of 0 is equal to equivalence class of 0. Equivalence class of 4 is equal to 4 belongs to equivalence class of 1, so it is equal to equivalence class of 1. And equivalence class of 5 is equal to equivalence class of 2. And then again equivalence class of 6 is equal to equivalence class of 0 equal to equivalence class of 3. And therefore after this particular point, what we get is only the rotation of equivalence classes we already generated. So naturally here we have only 3 equivalence classes: equivalence class of 0, 1 and 2, or equivalence class of 3, 1 and 5. An equivalence class can be represented or written using any representative element. We can write the equivalence class of 0 as equivalence class of 3, or equivalence class of minus 3, equivalence class of 9, all are the same. Anyway, here the set of all integers z is the union of equivalence class of 0, equivalence class of 1, union equivalence class of 2. And the intersection of any two of the equivalence classes, that is equivalence class of 0 intersection equivalence class of 1, is the null set. Equivalence class of 0 intersection equivalence class of 2 is the null set, and equivalence class of 1 intersection equivalence class of 2 is also equal to the null set. So that is how the set of all equivalence classes form a partition of the underlying set Z. So any equivalence class will form a partition of the set. You just try how the equivalence relation is going to be mod 7 form different equivalence classes on the set of all integers. Just try to write down all the equivalence classes of A is going to be mod 7. And also another thing, here we have only a finite number of equivalence classes, one equivalence class of 0, 1 and equivalence class of 2. In some cases we can have an infinite number of equivalence classes. For example, if you consider the set of all real numbers and the equivalence relation of equal to, then the set of all real numbers, if we consider a particular real number x, then if we collect all the real numbers which are related to x, then it is nothing but the singleton set x itself. And all the equivalence classes under this equal to relation is a singleton set, and there are infinitely many equivalence classes. So that's the nature of an equivalence relation, and I think that's enough for this particular class. So thank you.